Hello scientists, we're going to talk about the levers lab in Unit 6, but first we need to learn a little bit more about work and simple machines. The definition of work is the transfer of energy when a force makes an object move. Here's a cute little force making this cute little object move. In order for work to be done, the object must move in the direction of the force and move over a distance. So you can see that this pitcher is putting a lot of force behind a ball, and that ball is going to move over a distance between the pitching mound and home plate. So work, when we want to calculate the amount of work is done, is the force, that would be the pitcher in this case, times the distance. Force, of course, is a push or a pull, and distance is the space between 2 points. So let's see how we would measure that. Force we would measure in newtons, remember, and distance we are going to measure in meters. So if we want to measure how much work this weightlifter is doing, I kind of gave you a little bit of the answer here, we'd have to measure the distance that the mass traveled and how much force was used. So if you were going to measure the amount of work done by the weightlifter, you'd measure the weight and how high it was lifted. If you wanted to measure how much force the weightlifter had to exert, you'd measure that in newtons. Force, remember, is measured in newtons. And if you wanted to measure how far the weightlifter raised the mass, what unit would you use? This is what kind of stick. If you guess meter stick, you're absolutely correct. When we measure work, we measure force and displacement. And remember, those two units that we're using are, take a guess, newtons and meters. So when we multiply newtons times meters to measure work, that newton meter is called what? It's named after a guy who studied work, joules. So can we rearrange this formula to find force or distance? You betcha. If we divide work by distance, we'll get force. And if we divide work by force, we get distance. So there's a little bit of our calculations that we're going to do in the lab. The two labs that we're going to do in Unit 6 are about simple machines. One of them is about pulleys, but the lab we're going to talk about right now is about levers. All these objects have in common is they reduce the amount of force. They don't reduce the amount of work, they just simply reduce the amount of force. They don't reduce the amount of work. They do reduce the amount of force, or sometimes they reduce the amount of force. We'll check out pulleys in the next lab and see which ones reduce the amount of force and which ones don't. To get the same amount of work done, we reduce the force and we increase the distance. So simple machines reduce the force, but they increase the distance. So if you want to lift, say, a big rock with a small force, like your own force, you can use a long lever and increase the amount of distance you're exerting your small force. So, big distance, small force, same amount of work. You decrease the force, you increase the distance with simple machines. And you keep the amount of work the same. So here's a mathematical example. Let's say you needed to do 10 newtons of force times over 5 meters to get 50 newton meters or 50 joules of work done. Well, if you had a ramp, you could increase the distance here, but decrease the force. Like let's say you're pushing someone in a wheelchair up a ramp instead of the stairs. You have to go a longer distance, but you need less force. You do the same amount of work that if you had to lift them up the stairs. So simple machines make our life easier. I bet you haven't thought of a parking ramp as a simple machine. You have to increase the distance that you drive around and around and around in a parking lot versus, say, if you had a helicopter come and pick up your car. In this case, it's a tank, but if you had a helicopter come and just lift your car to the top of the parking ramp, you need a lot more force, but it would be a much smaller distance than driving around and around. We'll talk about this simple machine later. Levers are the type of the simple machine we're going to talk about. And you've probably had experience with levers in your everyday life. You may have played on something like a teeter-totter on the playground. When we put the fulcrum, the balance point of a lever, in different places, that we create different distances that we do work over. And if a lever here is balanced, it's doing the same amount of work on both sides. There are different masses you can see here, but since there are different distances, they're doing the same amount of work. Remember, work is force times a distance. Let's talk about the parts of the lever. There's an effort end that you press down on, and there is a resistance end. That's the mass that you're trying to move, and then of course the fulcrum is kind of the wedge point here. Here's a lever trying to move a big rock. The rock would be the resistance. This would be where you put effort in, and of course this is the fulcrum. The part of the lever where the load is, or the resistance, or the mass, is called the resistance arm. So this distance here is the measurement for the resistance arm. This part of the lever between the fulcrum and where you're putting in effort is called the effort arm. Now that we've done a little bit of learning about work, we can look at the lab sheet here and look at the equation for work. Well, we know that work is force times distance. The unit for force, of course, is newtons, and the unit for distance is meters. The unit for work is Newton meters, or we learned that we can also call that a joule. The point at which the lever pivots is called the fulcrum. That's the triangle thing that we've seen so far under the lever. Machines make work easier, but there's a trade-off. A machine reduces the force, so it reduces the force, but it increases the distance. The girl has more mass than the apple. There are two ways the girl and the apple could balance. One way to balance would move the fulcrum closer to. The other way to balance is to leave the fulcrum in the middle, but move the what closer to the fulcrum. Let's find out how to do this kind of thinking in a little bit of a simulation here. So here's a lever set up, and we can see if we put two equal masses here and remove the supports, it'll balance perfectly. If we move one mass in a little bit, the lever arm is different, so it's not acting with the same force. Even if we move it out here, it has to be way out here for even things to start to balance a bit. By adjusting where the mass is, it exerts different amounts of force, because remember, work is force times the distance. We can do something sort of similar to the girl and the apple here. We can take a very heavy object and give it a small lever arm, and give a lighter object here. The student weighs half as much as this teacher. We can take out the supports and they still balance. If we give the teacher a longer lever arm, then it doesn't balance anymore. The girl has twice as much here we'll balance it out a little bit again. The girl's mass is acting with twice the distance as the teacher, so they're still balanced. So we can see where the fulcrum is in relation to the mass makes a big difference here. We can do the same thing with bricks. If we put 20 kilograms very close to the fulcrum, and we put 10 kilograms, half the mass, twice as far away, it will still balance. If we change where the bricks are, it won't be balanced anymore. Even though this side has less mass, it's acting over a greater distance, so it's doing more work. So if we do a little bit of math and we multiply the force times the distance and the force times the distance here, we'll find out that 2 times 20 is equal to 8 times 5. You can figure number 9 out, and we will go to the Lever Lab and start filling in some of this data. So in order to get to the lab, go to 6.04, go to the 4th slide down here, and just click on this link right here. So in the data table, it asks us the first thing to do is use the 300 gram mass, put it at 60 centimeters, and measure the amount of force it takes to balance the lever. So let's pull down. And if you look at the spring scale right above where the green hand is, it says 3.17, and we're going to go enter that on our data table. Oops, stuff happens in the lab. So here we are back on the lab sheet, and we can compute the work done on the resistance side where the 300 gram mass was done just by multiplying the newtons times the arm length. I'll let you do that. And the pulling force here was 3.14 newtons. So the total force here, because we didn't need to pull down against the weight of the lever, is 3.14 newtons, because if we subtract A here, we just get 3.14 now, so we can multiply 3.14 times 0.6, and you can see that the work isn't going to be quite the same here as here, but it's about the same. This lab is not perfect. It should be exactly the same, but unfortunately things don't work out exactly the same all the time in the lab. Let's go do the second part, where we use arm length 0.2 and arm length 1.0, and I'll show you what that means in the lab. So we need to reduce and change the length of the lever arms here. We want to put this all the way to the end, so the lever arm where we're going to put the resistance is only 20 centimeters, because 60 minus 40 is 20, and if we add the 60 to 0 plus 0 to 40, this is a whole meter here. So it's a little bit confusing on the lab sheet, but I'm sure we're all smart people and we can figure it out. So I'm going to grab the 300 gram mass here, set it on the 60 centimeter line, and I'm going to have to pull up just to measure the weight of the lever. Let's make sure. That's 1.25 just to balance the lever with the mass on it. So 1.25 newtons. Oops, I need to let go here. What I should have done before I put the mass on is measured how much just the lever weighs. So how much force does it take just to pull up to balance the lever? and that's